Hello everyone and welcome to my presentation on ICP-MS techniques and their application in archaeometry. In this presentation I will first talk about some basic terminology necessary for the subject. Then I will describe the general setup of an ICP-MS instrument. Finally, I will present some applications of the technique for archaeometric research. First, let's start off with some basic terms. Atoms are the smallest divisions of chemical elements. They consist of a nucleus, which comprises neutrons that have a neutral charge, and protons that have a positive electric charge. Electrons, which have a negative electric charge, are bound to the core. Since atoms possess an equal number of electrons and protons, 8 each in the case of oxygen shown here, they are electrically neutral. Atoms with an unequal number of electrons and protons are electrically charged, positively or negatively, and are called ions. The oxide ion has 8 protons and 10 electrons, and therefore possesses a net electric charge of -2. Isotopes have the same number of protons and electrons, but possess a different number of neutrons. Therefore they have different atomic masses, and as a result differing physical properties. Oxygen atoms can have 8, 9 or 10 neutrons. Not only oxygen, but most elements have more than one isotope. Copper, for example, has 2 stable isotopes, 65 copper and 63 copper. Next, I will give an overview about the general setup of ICP-MS instruments. The abbreviation ICP-MS stands for Inductively Coupled Plasma Mass Spectrometry. This term includes the 2 principal components of an ICP-MS instrument. First, the sample is partially converted to ions in a plasma, or ICP unit. A plasma is a state of matter. It comprises charged particles, that is ions and/or electrons, and is therefore electrically conductive. The ions then are subsequently analyzed for their mass-to-charge ratio in a mass spectrometer, labeled here as MS unit. ICP-MS can be used for elemental chemical analysis as well as for high-precision isotope determinations. Different setup exists that are specialized for each of these applications. Furthermore, ICP-MS instruments can be coupled with variable sample introduction systems suitable for example, liquids and solids. This versatility makes ICP-MS one of the most commonly used analytical techniques in geochemical and archaeometric research facilities and commercial laboratories. In the following, I will briefly go through the principal components of an ICP-MS. The general setup of a liquid sample introduction system can be seen at the left. Liquid samples are pumped with a peristaltic pump into the instrument. This type of pump ensures for a constant flow regardless of, for example, the viscosity of the liquid. The sample is introduced into the nebulizer. There, an argon gas flow transforms the liquid into a fine aerosol. The principle is comparable to a spray can. The aerosol subsequently is transported into the spray chamber. It allows only small enough droplets to pass through to the plasma, because the plasma is not very efficient for larger droplet sizes. In total, only 1 to 2% of the sample therefore reaches the plasma. Another role of the spray chamber is to smooth out possible pulses of the sample liquid. Different geometries of nebulizers and spray chambers are available. The upper right image shows a common combination of nebulizer and spray chamber. The selection of the type of nebulizer and spray chamber depends on the analytical requirements and sample characteristics. Solid samples or sample surfaces can be directly probed by laser ablation for ICP-MS analysis. The general setup of a laser ablation unit for ICP-MS analysis can be seen on the scheme at the left. The sample is placed in an ablation cell that is movable in XYZ direction. The laser beam is focused on the sample to the desired spot sizes. The spot sizes typically are in the range of several 10 to 100 of micrometers. Small quantities of sample material are ablated with a laser, which generates a laser crater as in the image above. The sample then is transported as an aerosol in a carrier gas flow to the ICP-MS instrument. An example of aerosol particles produced by laser ablation sampling, seen under a scanning electron microscope, can be seen on the right. In the next step, the aerosol is carried to the plasma torch, where it becomes partially ionized in the plasma. A cross-section sketch of the plasma torch components can be seen on the left. The torch is made up of quartz and consists of an outer tube, a middle tube and a sample injector. It is surrounded by a radio frequency coil. To generate the plasma, argon gas is introduced between the outer and middle tube of the torch. An electromagnetic field is produced by applying radio frequency power to the coil. Free electrons are generated by inducing a high voltage spark. The electrons are accelerated by the electromagnetic field and collide with atoms of the argon gas. These collisions remove electrons from the shell of the argon atoms, thereby generating positively charged ions and further free electrons in a chain reaction. This process therefore is self-sustaining. The plasma forms at the open end of the torch. The photo on the right shows how an active plasma torch looks like. The sample is introduced into the plasma via the sample injector. In the analytical zone, temperatures are in the range of 6000 degrees Celsius. The interface bridges the ICP and MS units where pressures are at atmospheric level and at high vacuum conditions respectively. Its purpose is to sample and transport the ions from the plasma to the mass spectrometer. This is achieved by two metallic cones with small orifices, the sampler and skimmer cone shown in the sketch and example photographs. The skimmer cone has a much smaller orifice diameter and are usually sharper and steeper shaped than the sampler cone. Sampler and skimmer cones made up of different metals, for example nickel or platinum, are available as shown on the photo on the left. The role of the ion optic system is to guide and focus the ion beam to the mass analyzer. It therefore should ensure that a maximum number of ions is transported to the mass analyzer. Furthermore, it has to reject as many non-sample species, such as neutral species or photons, as possible. This is achieved by electrostatically controlled lens components shown on the right. The photo shows an example of a lens used in an ion optic system. The ion optic system is crucial for ensuring a low background signal and a high sensitivity. Mass analyzers separate the ion beam by mass to charge ratios. ICP-MS instruments with different types of mass analyzers are available. The selection of the instrument type depends on the measurement requirements and sample characteristics. A quadrupole is one of the most commonly used types of mass analyzers. The photo on the right shows a quadrupole mass analyzer from an ICP-MS instrument. The sketch on the left shows its design and functionality. It consists of 4 parallel metallic rods with equal length and diameter. They are used as electrodes, and the opposing pairs each have the same polarity. A direct current field is generated between one opposing pair of rods, and a radiofrequency current field between the other. Only ions with a specific mass-to-charge ratio can pass through the quadrupole. Ions with a differing mass-to-charge ratio get on an unstable trajectory and are ejected from the quadrupole. By varying the parameters of these electric fields, the ion beam can be filtered. Quadrupole mass analyzers have several advantages. They enable rapid mass scans and hence a high sample throughput, and offer low detection limit from the parts per billion up until the parts per trillion range. This renders quadrupole mass analyzers ideal for routine elemental analysis up to the trace and ultra-trace levels. The main disadvantage is the limited resolution, which also makes them more susceptible to interferences. Interferences can severely affect the quality of ICP-MS measurements. They are caused by the presence of argon, particular sample compounds, or by chemicals used in the measurements. The figure on the left shows a mass scan of deionized water with several peaks of mainly argon compounds present. Their masses overlap with those of elements such as calcium and iron. Several approaches exist to handle such interferences. If possible, element masses which are free from interferences can be analyzed. Interferences caused by elements with the same mass can be mathematically corrected. For example, the interference of 114 tin on 114 cadmium can be resolved by analyzing 118 tin, which is free of interferences. Taking the natural occurrences of these isotopes into account, the contribution of 114 tin to the signal measure for 114 cadmium can be calculated and subtracted. An important technique to remove interferences are collision reaction cells. They are placed in ICP-MS instruments before the mass analyzer. Reaction gas can be introduced into the collision reaction cell. It consists of a set of electrodes, such as a quadrupole, on which usually only a radiofrequency current is applied. It does not act as a mass filter here, but focuses the ions which then collide and react with molecules of the gas introduced into the cell. The example here shows the removal of an argon oxide interference of 56 iron. When the ions enter the collision reaction cell, it is flooded with ammonia gas. The gas reacts with the argon oxide to form atomic argon and oxygen and ammonia ions. The quadrupole of the collision reaction cell will then allow the 56 ion to pass along to the mass analyzer without the argon oxide interference. Several applications of ICP-MS techniques require a resolution that cannot be reached with a quadrupole mass analyzer. In these cases, instruments with a different mass analyzer type are used. One of the setups that enable a higher resolution is the double focusing magnetic sector technology. As can be seen on the sketch on the left, it consists of two analyzers, an electromagnet and an electrostatic analyzer, which are combined in a specific geometric constellation. The magnetic field separates the ions by their mass-to-charge ratio, that is, by energy to mass, and the electric field focuses the ions by their kinetic energy. The double focusing enables a significantly increased resolution in comparison to quadrupole mass analyzers, but has a notably slower working speed. Double focusing magnetic sector mass spectrometers therefore are commonly used for isotope analysis, for which a higher resolution is required. Detectors are the final compound of ICP-MS instruments. Their role is to convert the ions filtered by the mass analyzer into countable electric pulses. Different types of detectors exist. The functionality of some principal types are shown on the sketch on the left. Faraday cups, shown on the upper photo, are the simplest type of detector. The cups are conductive and produce a measurable electric current. The electric current is proportional to the number of incoming ions. Faraday cups require rather high ion currents and therefore cannot be applied for lower trace to ultra-trace element concentrations. Electron multipliers are another type of detector which has a higher sensitivity. They are available in different designs. The lower photo shows an electron multiplier detector with discrete dynode. The impinging ions create secondary electrons by collision with the dynode, that is an electrode within an electron multiplier. The electrons are accelerated to the next dynode, where they liberate further secondary electrons. This is repeated several times, and a pulse of electrons is generated. Finally, I will now discuss some applications of ICP-MS techniques for the analysis of inorganic materials in archaeometry. Research questions in archaeometry which are addressed by ICP-MS analysis generally concern the technology and/or provenance of materials. First, I will talk about the analysis of liquid samples, and then about measurements of material sampled with laser ablation units. For liquid elemental analysis of, for example, metal objects, the samples first have to be dissolved in acid, evaporated, and then taken up in weakly concentrated acid for analysis. With suitable dilutions, major to trace and even ultra trace levels can be determined. Quantification is done by external calibration. This means that relative element abundances in the samples are calculated from a calibration curve, as in the example shown on the right. The calibration curve is generated by analyzing standard solutions with known element contents, in this example for 10, 20, and 100 micrograms per liter, or ppb, and relate them to the raw intensity data produced by the instrument. Elemental signatures can be related to both provenance and technology. In the example diagram on the right, compositional data of source diagnostic elements silver and nickel in bronze objects are compared to data of ores from potential copper sources in Austria and Slovakia to support provenance hypothesis. Several elements determined in archaeological objects have an ambiguous character. Lead in bronzes can have been derived from the ore source, but it can also have been deliberately added to the alloy to improve its mechanical characteristics or to reduce the amount of more valuable tin. In the example for lead and tin contents in antique bronze coins shown on the left, a threshold value to distinguish between a geological or anthropogenic origin cannot easily be defined and might be further blurred by mixing and recycling processes. Isotope analysis from sample solutions requires the isolation of the target element. This is done by column chromatography. The photo here shows columns filled with anion exchange resin used to separate lead from sample solutions. In general, two types of isotopes can be distinguished from their formation: radiogenic and stable isotopes. Radiogenic isotopes are produced by the decay of radioactive nuclei. Variations in their abundances depend on the time passed and different geological processes. Elements with radiogenic isotopes that are used in archaeometry include lead, strontium, neodymium, and osmium. Relative differences in the abundance of stable isotopes are caused by physical, chemical, and biological processes. Stable isotopes of copper, iron, zinc, tin, silver, antimony, and mercury were already used in archaeometry. Lead is an example of a radiogenic isotope system which is frequently used in archaeometric research to reconstruct the possible provenance of artifacts. Its application is based on matching the lead isotope signatures of artifacts with reference data of raw materials. This is possible since the effect of metallurgical processes on the isotope signatures is not measurable or negligible. Lead has 4 isotopes whose abundances and origin can be seen on the sketch on the right. 206 lead, 207 lead, and 208 lead are derived from radioactive decay of uranium-thorium isotopes. 204 lead is primordial, that is, it is not radiogenic. The isotopic composition of lead therefore varies as a result of the radium-thorium-lead ratios of the source, or the sources, and the system closure time, that is the time when no further radiogenic lead was produced by decay of uranium and thorium. This can be equivalent to the geological formation age of metal ores, or a metal ore source in case artifacts are analyzed. But this is not necessarily the case, and model ages derived from lead isotopes and geological ages can be notably different, as can be seen in the right diagram that shows lead ore reference data from Europe with symbols colored according to major geological period. Since ore deposits are typically formed by large-scale geological events, isotope signatures are often overlapping and widely similar across country borders, as can be seen in the diagram on the left. Mixing and recycling processes during the production of artifacts can further complicate the interpretation of lead isotope signatures. Copper is an example for a stable isotope system which has been already used in several archaeometric studies. Differences in the copper isotopic composition are given as ratio of 65 copper to 63 copper and are compared to that of a standard and subtracted by 1. Copper isotope data commonly is presented in a delta notation, that is, the differences between sample and standard are multiplied by 1000. The isotopic composition of copper is strongly influenced by redox reactions such as weathering. This sketch shows the general behavior of copper isotopes in copper ores within a weathering ore deposit. In the uppermost outcropping oxidative zone, copper is leached and minerals from this zone are typically enriched in a heavy 65 copper isotope. As a result, the delta 65 copper is positive. In the underlying cementation zone at the groundwater table, minerals with a richer copper content are formed by precipitation of copper from the leached solutions. As a result, the copper content is higher than in the overlying oxidative zone, and the copper minerals are enriched in light 63 copper, and consequently the delta 65 copper is negative. The underlying primary ore has a copper isotope signature close to 0, since isotope fractionation decreases with increasing formation temperatures. Due to these specific differences between copper minerals from characteristic ore deposit zones, a reconstruction of the ore type is generally possible. The diagram on the right shows the copper and lead isotope variation in 4 series of Roman copper coinages, which are linked to different ore types and ore sources used. Experimental results demonstrated that the copper isotope signatures of ores and artifacts made from these raw materials are close to each other, while the copper isotope ratios of metallurgical byproducts such as slags in some cases may have been affected. Caution is therefore required for the interpretation of such isotope signatures. After talking about the analysis of liquid samples, I will now discuss applications of materials sampled by laser ablation. Laser ablation units can be coupled to different types of ICP-MS instruments to allow for both elemental and isotopic analysis. Laser ablation can be used to sample and analyze single grains or inclusions, as in this example on the left, where glass shards in plasters were measured for their trace element signatures. Furthermore, analytical profiles can be generated. The figure on the right shows a combination of trace element and isotope analysis by ICP-MS applied for the study of a fossil horse tooth. LA-ICP-MS has several advantages compared to classical liquid sample ICP-MS. It offers analysis with spatial resolution, and it can save time for laboratory preparation. In archaeometric research, laser ablation ICP-MS also is used for direct sampling and analysis of archaeological objects. Specific universal sample holders exist for these purposes, as seen on the left. Laser ablation ICP-MS is considered as a minimally destructive sampling method, as the craters typically are barely visible to the naked eye. The photo on the left shows an example of a silver coin whose surface was analyzed by laser ablation ICP-MS. This is the end of my tutorial. You can contact me per email if you have any questions.